Good morning, class. Today is October the 21st, and so this is the video for October the 22nd. And today we're going to first cover biofuels, but so a biofuel is basically taking biomass of some sort and making it into a fuel. Meaning generally taking some usually solid biological material and turning it into usually some liquid fuel. And so it's somewhat akin. Well, I won't write it down. I'll just say in words. I mean, you can think of it in the most general sense as being sort of akin to like coal to liquids, in the sense that coal is essentially a solid biological material, and you can have a process where a chemical process where you turn it into a liquid fuel, and so in a sense biomass. And there's many forms of this that can happen, and people are researching many forms to convert biomass into a biofuel. But we're going to focus on ethanol. And then here the biomass is some sugar, meaning glucose, which could be corn or sugarcane. And it's usually corn in the US and sugarcane in Brazil. And the idea is, okay, so first of all, ethanol is just like ethane. Okay, remember ethane, the alkane for N equals 2, and you just have 2 carbon atoms, and the only thing that's different is you put an OH over there instead of another H. And this is the same thing as you drink ethanol. All right, so how do you get ethanol? Well, from glucose. And so glucose, which is sugar of some sort, is C6H12O6. And so basically you take C6H12O6 and you have a chemical reaction where you produce 2 glucose, this is C2H5OH, and you get 2 CO2 molecules. And this is done using yeast, so fermentation. So, I mean, how does this happen, this chemical reaction? Well, I mean, I'm not an expert here, but basically, if you want to make ethanol, I mean, which a lot of people they do. First of all, you have to be careful, but I won't go into that. But basically, you have yeast. Yeast is a fungus. It's a type of animal, I guess. I forget the animal kingdom differentiations there between plant and animal, but yeast is a creature, a biological thing, and it basically eats glucose anaerobically. Can't spell meaning without oxygen. So yeast eats glucose and makes ethanol as its waste, so to speak. All right. So yeast does this. Now, what people do, right, is people take glucose and they eat it, and that means reacting it with oxygen. Just 6 people. So, I mean, when you eat glucose, okay, you react it in your body with oxygen, and this is an aerobic reaction. And so, when people eat glucose, they react it to basically to the final byproduct, CO2 and H2O. Of course, both of these reactions result in energy for the biological creature. In this case, people or animals in general, and in this case, yeast, these little fungus. So fungus eat glucose without oxygen, and the byproduct instead of water is ethanol. And so you can sort of think about it that what yeast do is take the energy in glucose and get part of it, but leave some fraction of the energy in the ethanol as a byproduct. And so, that's just how it works. Now, of course, you realize then that part of the process of making alcohol is you have to do it in a container or a tank with no oxygen, with no air, and so you can talk about. It's actually pretty interesting going to beer plants or distilleries and seeing the various equipment and tanks to make alcohol beverages. But basically that's it. Now, so you get the idea then that ethanol, which is a byproduct of yeast eating glucose, has less energy than usual fuels. And in fact, ethanol if you work out the chemical reaction. So this is making ethanol, and so now if I take that ethanol and I burn it, okay. So if I take that ethanol and now I burn it in a car engine, for example, in the presence of oxygen, I get energy, and and then you get CO2 and H2O, and you can work out that then that's 14. Oops, you know how to do this now. 14.3 eV. And so if you work out the numbers, then that's 28,400 BTU per kilogram ethanol, compared to approximately 43,000 BTU per kilogram for gasoline. Make sure that's all there. Yes, you can see it all. And so what you see is that ethanol has much less energy than gasoline. And so it's a known fact that if you run a vehicle with ethanol, and we'll describe vehicles in a little bit here, that you get worse gas mileage. So the gas mileage you get with gasoline is significantly higher than the gas mileage you get with ethanol. All right, so let's talk about ethanol use in this country. And there's a chart in the notes that shows that on a log plot. Okay, so this is ethanol consumption. In the U.S. Then on a log plot, so this would be 100,000 or 0.1, 0.2, 0.3, etc. Barrels per day. That went up exponentially. A straight line on a semi-log plot is an exponential, and then it turned over basically at around 900,000 barrels per day. And the reason it did that is because, okay, have you ever gone to your gas tank? Okay, so let's draw a little gas pump here with its display, and over here is the hose. I can't draw this. So here's a gas tank, or a gas pump, and the gas pump has a sticker on its side, and that sticker says 10% ethanol. And the reason, and if you've noted over the years, okay, I mean this break point occurred somewhere around 2010. If you bother noticing for the last 10 years, it's been 10%. And the reason why is that most U.S. vehicles can only tolerate 10% ethanol. And so gasoline consumption is about 9 million barrels per day. It has remained, fairly constant over that time, and so this is 10% of that, and it's just simple math. So basically, we consume this much gasoline, and 1/10 of that is ethanol, is what it comes down to, and it's limited to 10% because most U.S. vehicles can only tolerate 10% ethanol. Because ethanol is corrosive, and so unless your engine is specially designed for ethanol, that's as much as you can have. And now there are what's called E85 vehicles, which have special engine components to tolerate ethanol. Okay, but it's about 3% of the vehicles in the U.S. So there aren't very many of them, and so most vehicles can only tolerate what's called E10, or 10%, and so that's limited ethanol use in our country to about 900,000 barrels per day. And now there's a push to increase that to 15%, That push has been around for a few years now. Of course, in the U.S., ethanol is made from corn ears, and corn producers, or the ethanol community in general, would like to increase this limit higher, and so they'd like to increase this to 15%, and very new vehicles of the last few years, I believe, are designed to tolerate slightly higher ethanol composition, about 15%. The problem is that vehicles, older than 2010 or something, or even 2015, can't tolerate any more than 10%. And so it's sort of a problem that, okay, in principle, at your gas station, there could be a pump for 10% ethanol, and there could be another pump for 15% ethanol. In principle, there could be a pump for 85% ethanol if you had an E85 car. And gas stations aren't going to do that because it's like, okay, then you sort of like have this proliferation of gas pumps, and it just is kind of logistically a problem. And so basically we're limited now. Now, so how does it work out in quads? Well, basically, so this is about 0.9 million barrels per day. Times, okay. If you take 28, okay, let me first do that calculation. And I'll just write it down. A barrel is 42 gallons. And so if you work out the density of ethanol from 28,400 BTU per kilogram, it works out to BTU per barrel. All right. So if we have 0.9 million barrels per day times 3.2 million BTU per barrel times 365 days per year, okay, it works out to around 1 quad per year. So that's our current consumption of ethanol, is about 1 quad per year. Now, in your final project, you can enter a different number. And so this is giving you all the facts behind what has to go into that number. So basically, pretty much, I mean, that number can be increased in terms of we can produce more ethanol probably. But the limitation right now is most of our vehicles can only tolerate 10%. And so to a certain extent, it's kind of a chicken and an egg problem. We could have, I'm not exactly sure why, okay, the break point is then 10%, then 15%, and then 85%, why it works out like that. Now in Brazil, most of the vehicles are E85, and so they actually consume far more ethanol than gasoline. But here it's sort of a chicken and an egg problem where the limiting step is to a certain extent the gas stations. And the gas stations are like, well, okay, we have to put in a new pump, okay. And in some places they do that. Every once in a while you see an E85 pump. But in order to go up from 1 quad per year, that's what has to happen. And it's kind of like, okay, I remember, say, around 2005 or so, you would see advertisements from car makers touting yellow. I mean, yellow was the color for going to ethanol, and they were promoting E85 vehicles. Now, E85 kind of never took off because, to a certain extent, people knew that you get worse gas mileage, and so it was kind of like, well, all right, I'm kind of paying the same amount for this liquid, which there are subsidies, and we won't get into that. But people were sort of turned off because, well, you know, I mean, it's kind of inescapable. The gas mileage is going to be lower, and so you know, no, this did not take off here in the U.S. People continued to burn gasoline vehicles instead, and what happened basically was electric vehicles came along. And so with an electric vehicle, okay, there's no limitation at the gas pump. I mean, the gas pump's not involved. And so the infrastructure was at rather a change into charging stations, which to a certain extent electric vehicle manufacturers were willing to do on their own, independent of the gas station. And so the ethanol kind of, you know, had a kind of a log jam that could not be overcome. Now, okay, so basically, in your final project, you have all the information here to go off and do research and predict whether that number. Now, in the final project, that number is going to be for biofuels in general, of which ethanol is only one. It's the only one we use in quantity. The notes also discuss things like biodiesel, and you know, biodiesel is fabricated from vegetable oil, and so you know, that could be something that takes off. Right now, as it's shown in the notes, there's almost a negligible amount of biodiesel used in the country, but that's what I wanted to present on biofuels, so you understand the concept. Now, one final discussion is that the process. Okay, so what you see basically for ethanol made from sugar, from glucose, is that you get part of the energy in the glucose, and roughly the efficiency is about 0.4, meaning the efficiency, so here you have a certain amount of energy converting. Okay, so because I could just burn that glucose, right? I could burn it here and I could get all the energy in it. All right, converting it to a fuel, you lose essentially 60% of the energy, roughly. And that number's in the final project file, and we'll go over that when we go over the final project. But so basically, going back to biomass, one route we considered was taking the biomass and burning it in an electric power plant to make electricity, and then you get all of the energy in the biomass. Of course, there's a conversion in the power plant and things like that. But then we have to drive electric vehicles, all right? So biofuels is a route where we don't have to drive electric vehicles. We rather convert it to a fuel and then use our internal combustion engines like we have been. So going that route, okay, you lose part of the energy, and so it's an overall system question of what you want to do. All right, and that's all I was going to cover on biofuels. And it sort of leads us into our next discussion, which is engines. And because, you know, what we just said is that you make a biofuel so that you can operate a vehicle with an internal combustion engine. Now, I know the quiz is a week from tomorrow, and so we're just going to get started on engines. Basically, heat to work. So we've discussed all these energy sources, including ethanol, which basically are sources of heat because you can burn them. And so we want to know how we convert that. Okay, so you make an engine. Okay, and the idea is that, all right, an engine consists of a cylinder and a piston. All right, and let's draw more of it. So you have a cylinder and a piston. All right, and let's put a linkage up here to another linkage. And we're not going to get into transmissions and stuff like that, but basically, keep losing my chalk, as this goes up and down, that, you know, you arrange it so that when it goes up and down, and so you have a mechanical linkage here so that this up and down motion gets turned into a circular motion in your car or the drive shaft. And why does it go up? Because you put in heat. Now, there's two forms of engines. There's the external combustion engine. And that's where the heat comes from outside. The cylinder. And then there's the internal combustion engine. Internal combustion engine, which usually you go by the acronym ICE, or the heat in cylinder. All right, and after the quiz, in the first lecture after the quiz, we'll go into more detail of how that happens. But basically, heat causes the gas to expand. Pushing piston up. And so that's the energy conversion process. Okay, you put heat in somehow, it pushes the piston up, and you get the idea this is a cyclic thing, it has to come back down, and so I'll explain that in a little bit. But basically, this process, you know enough to characterize it with what's called a pressure volume diagram, where in that space there's a pressure P and a volume V that both are functions of time. Okay, I'm not going to write P of V and T, okay, because there's no reason to. But basically, if you put, let's say the piston is at this location, where it's near the bottom, it's at its maximum compression. Okay, minimum volume, and you put the heat in. Well, pressure goes, volume goes up, and I'll explain what happens now. So basically, let's say we start at the minimum volume maximum pressure point, like that. All right, and now what's going to happen? Well, okay, so I'm going to draw a curve here where I'm inputting heat at constant temperature. Now, how will I do that? I'll explain that in the next lecture. But what I want to get at here is that, okay, I put in heat, and what happens, and I hold that heat, that heat input at a constant temperature, and I'll explain how I do that in the next lecture. And so pressure goes down as volume goes up, and you know how, okay, because, okay, for that step, remember P is proportional to T over V. So at constant T, P is proportional to 1 over V. So that part of the curve is proportional to 1 over V. And you do that for a while, and then you take away the heat. So what happens then is this goes down faster, because now, okay, you take away heat, there's no heat, T goes down, and so because pressure is T over E, this goes down faster than 1 over V. So this is 1 over V, and basically you can write this as 1 over V of 1 plus some number A, because temperature is going down in this step. All right, now what happens? Okay, then you reach, okay, this is the point of maximum volume, minimum pressure, so basically at that point the piston has gone up to its highest point here. Okay, the volume is at its maximum, the pressure is at its minimum, and then I'm going to write it as you input cold. Okay, you know, here you inputted heat, and then here you input cold, and the idea is that let me draw this better. You know it's what part of the curve it's associated with. All right. Okay, so at constant T, can't draw with crowd. All right. All right, so how does that go? Well, you know how, because if it's constant T, this is going as 1 over V. All right, and then in your fourth step, you take away the cold, T goes up, and so then this goes up faster than 1 over V. Basically, it's 1 over V of 1 minus A, so to speak. Because temperature is going up during this step. So if temperature is going up, I'm going up faster than 1 over V until you reach the point, and everything is designed so that it goes in a cycle like that. The piston goes up, up, down, down. And now, let's talk about what you know. Energy and I'm going to write it out because of how you know, are really supposed to it, is force times distance. All right, and it's the integral. So it's the integral of f dx. But pressure is force per unit area. So it's the same as the integral of f over a times a dx. But that's dv. So it's integral of, this is p dv. Okay? Now I realize this is a lot to take in, especially if you've never had, you know, engineering classes like this. But, okay, the point is that when the piston is going up, okay, when the piston is going up, there is work being done equal to the integral of these curves. So it's equal to the, now remember what the integral is, that's the area under the curve. All right, now, when the piston goes down, the work is being done in reverse. The piston is doing work on the gas. It's putting energy back into the gas, so to speak. And so the work being done by the gas on the piston is the integral of that. And then the work being done by the gas on the piston, or the negative work, is that. And so the net work, okay, net work is that area. And so you can see that the whole idea with an engine is to get a PV cycle where it traces out an area in the PV diagram. See, if you went down and up on the same curve, there would be no work being done. All right, let me draw that over here. If I made some stupid engine where, okay, it went down that way and went up in the same curve, all right, if I went down and up in the same curve, the work being done by the gas and the piston in this step would be canceled out by the work being done by the piston on the gas in this step, and you'd never get any work done. No energy would be being transferred to your car's wheels. That, if you somehow stupidly make that sort of engine that did that, you would not get any energy. So you have to design a cycle, which I've sort of given you the idea here of how you do it, where this traces out an area in between the curve, and that's your net work done per cycle. Okay, and we're going to stop there. That's the up to the quiz, what I expect you to know, and we'll talk about it more in chat class tomorrow.